presenting.
Yes. Thank you, Mr. Lillot. Good afternoon, ladies and gentlemen. I'm going just to tell you about an overview of what's rapid prototyping. And first, I will present my company, and then I will give you an introduction of the general principle of rapid prototyping. Then I will see with you in details several rapid prototyping techniques that can work with nanoparticles. And then I will summarize this during the conclusion. And first, who is Sirris? This is a research center with approximately 1,500 industrial members. It counts 6 sites in Belgium and 140 workers. Most of them are engineers. There is 2 sites in Wallonia. I work for Sirris Wallonia. And the objectives of the research center is first research, and then we also provide services for our members, and we do also technology foresights. And we have 4 centers of competencies in Wallonia. First, the bigger one is materials engineers. We have a rapid manufacturing department, a patent office, and a small team of technical assistants to provide services to our members. With the rapid prototyping department, we do some prototypes. Prototypes can be visual prototypes, when the guest only wants to have a real shape in his hand, to check his shape, check his functionality, or check simply how does it work in a process, just to really check the part before starting the production. And we can also make some pre-series. We have several machines that can use different types of materials: plastic materials, metal materials, and ceramics materials. We have also a team that will develop some new materials on the machine and will optimize new processes of a machine. And we're doing also rapid tooling. What is rapid tooling? It's rapid manufacturing of a mold with special feature. We do this in collaboration with mold makers. And we can work for a wide range of different kinds of industry. We work for automotive, for aeronautics, for aerospace, military, electronics, customer products. We can do very different kinds of parts. Let's see now what is rapid prototyping. We have to see rapid prototyping beside another technique well known is traditional machining. In machining, we will start from a block of materials, and we will remove materials with cutting tools. By milling, drilling, cutting, we will shape the desired part. But there is 2 drawbacks of this. We lost of material, and we can do the shape. We can do every shape we want. We have a limitation of the shape. Thus, in rapid prototyping, we build the part step by step by material addition. So we will start from a raw material. In this case, we start from powder, and we will build step by step final part, directly the part with a limited quantity of waste, and we have no shape limit for this. Virtually, theoretically, we have no limit, but there is some parameters that will limit the shape we can do. How does it work? We always start from a 3D CAD files, and these files will be sliced in 2D slide of adjustable thickness, and these slides will be sent to the machine, and the machine will build the 3D part by adding all these 2D slides. And we can do very complicated shape, like this. Here we have what we have called rapid tooling. It's a mold with a very special feature, what we call conformal cooling. There is a cooling channel that follows the shape of the part inside, just under the surface. And we can do this by traditional machining, but it's possible to do them by rapid prototyping. We have also another part here, metallic part, with a very complex shape and helicoidal cooling channel inside. We can do internal structure, 3D structure like this, or simply art part with very complicated shape and very different kind of materials. We have different kind of techniques that work with different kind of materials. The building techniques will build the part step by step by, for example, by using a UV polymerizing laser, thus starting with a liquid resin or a paste, which is a blend of resin and powder. This paste or resin is photo-curable, thus when it's exposed to the laser, it will polymerize, and we progressively build the part layer by layer. Another technique is laser or electron beam melting. In this case, we will start from powder, polymer powder, metal powder, or ceramics powder, and a laser will melt locally the powder to build each layer of the part, and part will be built layer by layer too. Instead of melting, you can have laser sintering or printing a binder. This binder is really print as like in print desktop. Because we have a printed print binder on the powder bed, and we stick the powder locally, and then we have to debind and to sinter the part. Thus, I have already said, the building is done by repeating step of spreading and lasing or melting. We're spreading a layer, and we build one layer, and we repeat it, this step, as many times as there is a layer in the part. There is a relatively new technology called cladding. In this technology, we have not two steps during the binding. These two steps are being done in one step. This powder is directly injected in the torque, and the part is built directly on the plate. There is no step of spreading and building. It's all in one step. Let's go now for an overview of four different technology of rapid prototyping that can use nanoparticles. First, I will see the Viper stereolithography. Then I will see Optoform process, then 3D printing, and finally bioplotter. Let's go first with the SLR Viper, which is a high-resolution stereolithography. This technology is sold by a company called 3D System, and by using this technology, you can do a part with very, very small details with a UV photo-curable resin. Here is a sham of the machine. We have a platform on which the part is built, and this platform is immersed in a bath of liquid resin. And the platform will start on the top of the liquid base. It will fall down of one increment. This increment has the size of one layer. Then a sweeper will pass above this platform and will homogenize the size of the layer, the thickness of the layer on all the platform. After this, a laser will draw the first layer of the part on the platform, and when the resin is exposed to the UV laser, it will polymerize and progressively build the part. And next steps, the platform will go down of one increment. Sweeper will pass above the platform, homogenize the size of the layer, and then laser will build the second layer of the part, and step by step, by repeating step of spreading and lasing, we will build the final part. But there is two problems of this. With this, we have to add some support between the platform and the part, because if we build directly the part on the platform, we won't be able to take the part off, because it will be stick to the platform. So we add some support. Support are structured like this. It's a very thin structure that are strong enough to maintain the part inside the machine, inside the bath. It's weak enough to can be easily cut after building to extract the part. We have also a problem with all cantilevered and overhang structure on the part. Because of the resin is a liquid, it doesn't sustain the cantilevered structure. They need to be supported too, as we add some support between platform and this cantilevered structure. All this support have to be added to the cat file before slicing. Then we have the step of slicing with the support, and then part is built with its support inside the machine. Here are the features of the Viper stereolithography in high resolution mode. Thus we have a laser beam thickness of 75 microns. The thickness of the layers are in the range of 25 to 50 microns, and these features can reach an accuracy of approximately 0.1 millimeters for small details required by some medical application or electronic application. And the maximum size of the part we can build with this technology is a box, a cube of 250 millimeters side. So one important feature of this machine is that that can use different vat containing different kind of materials, and we can change this vat of materials to build some different kind of materials. So we can build rigid or limp materials. We can build some part with clear or opaque materials, and then after building we can apply some different finishing, treatment, painting, varnishing, coating to really build a prototype, a functional prototype in some case, with a clear resins or opaque resins, or with a color treatment after building. Thus, with this technology we can make some composite parts. The interest of doing a composite is to improve the properties of the final part. Thus the company DSM Somos produced a new resin called Nanoform. This resin is a thermosetting polymer that is loaded with silicon oxide nanoparticle. These nanoparticles will increase the strength of the final part, increase the thermal resistance of the part too, and because of the small size of this particle, there is no settling inside the uncured resin, so it's a stable product. And because of this very small size of the nanoparticles, it can run in a high resolution mode, thus we can produce very small details in the part. The second technology we'll see is Optoform. So Optoform is a process we call direct composite manufacturing process. It has been developed by a small team of French researchers. And once it has been developed, this team sold this technology and patent to 3D Systems, who commercialize now the machine. Until now, it's only a research machine because there is lots of parameters to can produce good parts. It's a limited application, but we can use a large range of materials. It's its main advantages. And we have about 10 machines all over the world at the moment. How does it work? As previous, we have repeated step of spreading and lasing, but we don't use only a resin. We use a paste, a blend of resin and with a filler, what about 20% to 60% in volume is occupied by the filler. The paste also contains a photoinitiator. This photoinitiator will react with UV laser and initialize polymerization. It contains also wetting agent because to have a good final properties, we need a good wetting of the filler by the resin. And finally, we add also some rheological agent that will fix the consistency of the paste. The paste must be like a toothpaste because it has to sustain itself on the building plate, but it needs also to be well spread. The viscosity has to low when there is a shear stress applied during spreading. Thus, we need this thixotropic behavior to have a well spreading of the paste on the building platform. So here is a scheme of the technology. So we have a building platform that starts on the top here, and a recoater that will spread a layer of paste on this plate, building plate. After this, a layer will draw the first layer of the part, and then recoater will spread the second layer of the part, and UV laser start to lase, to build the next layer of the part. And by successive steps of spreading and lasing, we can build very complicated shape and inside this paste bed, this paste plug. But once we have built the part, we have to extract it. Because here, as previous technology, we need some support between the platform and the part to can easily extract it. And we need support under every cantilevered structure of the part because the consistency of the paste don't allow us to build, to sustain the part itself. Because all this composition has to be fixed to have a good lifetime of the paste. Look, we can't have settling of particles inside the part because this will lead to ununiform dispersion of particles inside the paste and inside the final part. And there is another problem that appears with this technology. The fillers can't absorb the UV ray because it will lead to a phenomenon we call screen effect. If the filler absorbs the UV laser, the energy contained in the UV laser isn't used to polymerize the paste. Thus, we will have polymerization only on the surface of the paste bed, but not inside the paste bed, and we won't have a good reaction between the layer, and the part will collapse after building. So I've said we need some support to sustain the part, but after this we have to clean the part. It's a very tedious work because paste is very sticky. Okay, stick to the part, and we have to extract it manually by using solvent, sometimes organic solvents that are not very healthy, but it's the main drawback of this technology. Different features of this technology are a layer thickness of about 35 to 100 microns. The laser is an argon laser of 100 to 800 milliwatt. Maximum size of the part we can build is a box of 250 by 350 by 500 millimeters. This technology is very well suited to build small parts made of inexpensive materials, as well as massive tools made of cheap materials. Thus, we can use a very large range of different materials. But we need some support to sustain the part inside the paste. So we can use 4 kinds of materials. We can use plastic, rigid plastic or soft plastic, or we can build some metallic or ceramics parts. Until now we have built stainless steel, titanium, alumina, zircon, silica, silicon carbide parts. But once we have built this, we have a composite, a polymer load with metal or ceramics particle, and we have to debind it and to sinter it after shaping. So the state of the raw materials allows the use of nanoparticles, because nanoparticles will be stabilized inside the paste, and these nanoparticles can be used to improve sintering or improve final properties of the part. Depends on the case with today. So for nanocare project, we developed some ceramics paste using nanopowders, so alumina paste and silicon carbide paste. We'll start for alumina paste. 2 different pastes have been done. One paste is made of submicronic alumina, and second paste is composed of 90% submicronic alumina with an addition of 10% nanometric zircon oxide. So this paste is very reactive because these 2 components, alumina and zircon oxide, are clear to UV. Thus there is absolutely no screening effect in this case. And parts were sintered by INSA in Lyon, and we reached final density of 94 to 96%. And we have some example here of the parts that have been done. So we have knee or hip prosthesis or dental prosthesis made for Nobel BioCare. Silicon carbide. So we have tried to build parts using this powder composed with the paste. The filler of the paste was compound of 70% of 25 micron silicon carbide, 16% alpha silicon carbide, submicronic particle, and 14% nanometric silicon carbide particle. By using directly this composition, this will lead to a very important screening effect, because the silicon carbide is absorb UV beam. This effect is increased by the presence of very small particles. So we have to add these 2 components, yttrium oxide and alumina. These compounds are clear to UV and will lower this screening effect and lower also sintering temperature because they are melting compound in this case. Thus, we can do liquid phase sintering with this part. They have been sintered at about 2000 degrees at IFKB or IFCT in Germany. The example of part we made are shown here. We have several technical parts, and this part was made for NanoCare project. It was a honeycomb support for a spatial mirror, and we reached final density of 88%. This is what it was not very bad, but not very good too. Because we can increase this final density by increasing the concentration of filler inside the paste. So it will perhaps increase the final density by this way. Another technology is 3D printing. In 3D printing, we are going to build the part layer by layer as previous, but this time by printing a binder or special agent. When we print a binder, we can produce a part, this what we call rapid manufacturing or 3D printing, or we can start with electronic card on which we are going to print some special agent or special materials, only one layer of these materials. That's why we call this application 2.5D printing. Or why is it called 3D printing? Because it uses exactly the same technology as an inkjet printer. So with lots of common parts with this technology. This 3D printing has been developed by MIT in the United States. They switch the patterns into different kinds of materials. They sold patterns using gypsum powder to Z-Corp Corporation. Z-Corp will use 3D printing of gypsum powder to create some visual prototype or to make some casting molds. Just by using gypsum, it will print with a white binder to have this kind of part, only visual part. It can print a clear binder with color inked with the binder to provide a part like this, a colored part that can be used as a visual prototypes to really show inside of a showing part for exposition, or simply the guest can have the part in his hand to check the functionality of it. The other pattern concerns metal powder. It was sold to Prometal X1 company, and this Prometal used 3D printing to build real mechanical prototypes that can be really used in specific application, or to build small series of very special parts, or simply artist parts like this. So part you can't produce by another way. You can't produce this by traditional machining. How does it work? As previous, we start for a CAD files, and we will, in the machine, we have a building plate and a feed box. First, the building plate will go down of one increment. This increment has the size of one layer, and a spreader will spread a layer of powder on the plate. Then the printhead will print the picture, the first layer of the part. Then we have the drying step. This will, because the binder is a solution, is a binder with water. This drying will evaporate the water, and it will only stay the binder that will stick all the particle between them to shape the final part. And step by step, the part will be built just by repeating, spreading, printing, drying, spreading, printing, drying. Just we can build very complicated shape by this way. There is two kinds of printed, what we call continuous jet printed, that can use in high-speed printing, like printing of newspaper, for example. It's the same technology used here to build very fast building part. Or there is another technology, printed drop on demand. This is a lower speed building but higher accuracy. It's technology you find in current inject printer. So once you have built the part, it's completely immersed inside the powder bed. It has to be extracted, and we have to clean all the powder that's around the part and inside small channel inside the part. And then we have to debind and sinter the part. So there is only one limitation, one requirement for this technology. The powder must be well wetted by the binder, because if not, when you print the binder, it will stay binder droplet on the powder bed. The binder won't percolate inside the bed. You won't have a good sticking of the particle and a good sticking of the layer between them. So this technology can also be used with nanoparticles to improve, as previous, to improve sintering or specific properties of the final part. So we can add nanoparticles in the powder bed, but with the volatility of this powder and the fact that the worker is always in contact with unprinted powder, it's too dangerous, it's too hazardous to use in powder bed, to use nanoparticle in powder bed. We forget it. But we can add nanoparticles inside the binder because of the size, very small size of the particles. It can be passed through the printed. Thus, inside the binder, nanoparticles will be stabilized, and we have to check if there is no settling inside the solution. And we can also add some other things by the same in the same times in the binder. The last techniques is what we call bioplotter. It's a technology sold by Envision Tech. But first, it was initially developed to build some new organ. But it was working by local injection of a cell culture in a nutrient gel. Just by using needles, there will be injection of cell culture with nutrient gel. And by using different kind of cells and different kind of nutrient gel, this will lead to progressively a cells differentiation. And finally, we can create new organ with very specific function. By using this technology, human skin have already been built, and several tests are currently being done to make other organs, like liver, for example. And this technology can be extended to high viscosity materials. Thus, we can replace the needles by an extrusion screw. Thus, we can have a local extrusion of a cylinder, and this cylinder will be used to build the final parts as previous, layer by layer, and here line by line. Thus, we can dispose different cylinders side by side to have a full dense part, or we can let a specific void between them to make a porous structure. We can also use different kinds of materials by using different head. Thus, we will spread first materials, then we can change the head, spread another materials, and also apply different texture to the part. And what is important here is that we can use different kinds of materials too. We can use melt polymers, we can use slurry of metal or ceramics, or we can use composites made of metals or ceramics, particles loaded inside the polymer. So we do, in this case of composite, we can do ceramics injection molding. So we could have a local extrusion of a cylinder made of this composition, was made of a blend of thermoplastics loaded with micro or nanoparticles. And these nanoparticles can improve sintering and properties as previous. Thus we will local extrusion of a part of a thin line, and by repeated step of lining, of extrusion this line, we can build one layer of the part, and by repeating these steps, we can build progressively layer by layer final parts. But this part is also a composite part, thus we have to debind it and to sinter it after. So, yes. So, summarize now. We have seen that rapid prototyping technology are very suitable to build some prototypes and very small series of parts. This part can have a very complicated shape. It's not a problem. We can do, theoretically, we can do every shape we want, but there is some limitation due to some of the techniques we will use. The parts are made layer by layer by material addition in opposition to traditional machining, in which the parts are made by material removal. And we have seen that some techniques can run with nanoparticles to improve some properties of the final part, or simply to improve the sintering steps that is needed with some techniques. So with the Viper stereolithography techniques, we have nanoform resins, which is a blend of thermosetting polymers with nanoparticles of silicon oxide. And we can keep the high resolution mode of the stereolithography. Look, we can build very detailed parts with an improved strength and thermal properties higher than current resins. With Optoform technology, we can add some nanoparticles inside the paste. They are stabilized inside the paste. There is no settling inside the paste. And this will improve, the nanoparticles will improve the sintering of final step of sintering and final properties of the part. We can add nanoparticles to have very particular properties in the final part. 3D printing, so we can add nanoparticles inside the binder instead of inside the powder, because it's too hazardous because of the volatility of nanoparticles. They are not in a stable state inside the powder because they are exposed to atmosphere. And finally, by using bioplotter, we can do ceramic injection molding of thermoplastics load it with nanoparticles, microparticles, and this will lead to improving sintering of final property too. So, thank you very much for your attention.